All right, number 10 is an interesting minor variation of number 9. Instead of 3 to the positive x, we have 3 to the negative x. So if you plug in negative 2 for x, you get 3 to the negative minus 2. So you get 3 to the positive 2. Two negatives cancel each other out. So you get 9 for the y value there. And when you plug in x equals negative 1, you get 3 to the 1, so that's 3. 3 to the negative 0 is still 3 to the 0, so that's just 1. Then you get 1/3 and 1/9. So now think about this. As you come from left to right, your y values are starting high and coming low. As they come low to the right, they're getting smaller and smaller. But again, they'll never hit 0 and they'll never go down below 0. So we'll have a horizontal asymptote at y equals 0. Scale the y values up to 9. X values from -2 to 2. And then when we plot this, you'll see the curve is similar to what we got for the last one. The graph is just flipped over the y-axis. So it's kind of interesting. If you take a function, an equation, and you multiply it by -1, then that reflects your graph over the x-axis. So if it was above, it flips down below. But if you take an equation and you replace just the x value with -x, then instead of flipping over the x-axis, it flips over the y-axis. Because it's treating all of the positive x values as negative now, and the negatives as positive. So that's what we get here. And we'll call this exponential decay. We haven't seen a model that does exponential decay yet, but they're very important in applications. For example, radioactive decay is an example of exponential decay. And we use that for carbon dating, or scientists use that for carbon dating. You can measure how much carbon is in something and figure out roughly how old it is because you know how carbon decays over time.